Good afternoon, gentle readers. Today is September 3rd, 2024, Tuesday. From a desk with Ross Finlayson, speaking, Seattle, Washington. Today's topic is moment in motion, punctuation. So, the notion that I've been arriving at over the past few and many talks is this, that 0 meters per second is infinity seconds per meter, and that we have a very well-explored school of the mechanics and the theory of the mechanics of motion, and that's physics, that's classically mechanics, the physics. So there's these infinitely many higher orders of acceleration, and it's just a bit less well explored. So all the way at the other end of Zeno's thought experiment, where on the one hand it's the smallest, the longest journey begins with the first step, this kind of thing, the small end, the little end. As with regards to otherwise, it's like we can only take off as big a bite as we can chew at a time, the big end of the geometric series, the infinite series of the negative powers of 2 that sum to 1, or Zeno's example of the geometric series that's convergent, has a limit, and the limit exists, and it reaches its limit, is basically a matter of what's considered fact here, mathematically fact. It is so that mathematics is a different realm than science, while at the same time they're both inextricably linked, because our study of it is as of a science, while what it is as of a fact, a mathematical fact. This is called strong mathematical Platonism. Of course, it's the theory that humanity writ large has had since about 200 years ago, two millennia. That since the time of Aristotle, it's more or less kind of so that Platonism has got this metaphysics associated with it, that it's real and beyond the realm of our phenomenology and senses, with which we make a survey and make an ontology of it, and make a science of it, make a language of it, and make a theory of it. This is what we may arrive at, as much as we may attain to, reaching toward to attain this theory, that we may obtain all its significant results. As with regards to the universal success of mathematics and physics, that it really kind of makes for why it's so compelling for people, and it's to be known for its own sake, and that it will always be true to you or anybody else in much the same terms, that it's this universal language of mathematical fact. So in the theory then of the motion, and to ascribe to what we have our mathematical models, which is any kind of system of relations and terms, then the physical models, which is associating that with objects that we can establish as part of our objectively shared reality, that then for our scientific method, which involves falsifiability, observability, and reproducibility, that it's possible to establish from observability that you get measurability and the quantitative and the exact and the quantitative, and then within those bounds then we can make for what really is, as far as all can not have their illusions dispelled, what is mathematical physics. So with that kind of airy and brief introduction to the overwhelming priority of why that's the thing, then we kind of get back to what we started with the tools that everybody has, and then how those are put together. So what that is a measuring stick and a stopwatch. So these two being able to establish the metric and norm, being that the metric is what you measure and the norm is what you extrapolate. It'd be the same everywhere else, where the metric and the norm exists all the way throughout forever, the space, the time. And then it was with regards to the issues of that happen in the real, in the space contraction with length contraction and time dilation together, making that motion makes space contraction. That this then gets into some of these premier theories of the time, Einstein's relativity, and preferably his more thorough, fuller total field theory, which he calls one theory of relativity together, that he developed from his initial forays into the studies of the Lorentzian transforms and Lorentzian invariants for special relativity, and then later general relativity, with the usual notion of the geodesy and this kind of thing, and then figuring out with among all these other people who understood these theories and their mathematical models and physical models that time dilation would be a thing and length contraction would be a thing, and then as with regards to the experiments that at least make it closer to what's so. If for example, when it was measured the distance of Mercury right off its predicted value, and it was so close and yet closer with this theory of relativity, let us know that it's just even a little bit more than that today. That it's so that's classical in the limit as well, that it falls back down, and as the metric exists and the norm exists when everything is still and quiet and easy to articulate. And then these are some of the greater features of the theory, the superclassical features of the theory. The flip side of that is usually, of course, the particle wave duality. And so that's kind of how I was thinking to approach this idea of the punctuation of continuous motion. And when it has any moment is when it changes at all, and in its inflection or as of a stepping stone, that's a point where it rests, so that this point or the punctuation is as of then otherwise this continuous thing of the idea, for example, when a quantum wave, which is all the possibilities, collapses to an event, and of course it immediately expands again to the resulting set of possibilities by that action, the least action, the sum of histories, sum of potentials. That what gets arrived at is that this idea of the punctuated motion then is, first of all, it's a concept that already exists. When you explore the field, you start to find references to this kind of thing that help explain that what it is for our classical laws of motion, like rest, motion, equal, opposite. Next to that, force equals mass times acceleration. It's just like this is our proportionality constant, and this is also happens experimentally to hold. Then inertia is linear, which is great. Then gravity being on the side of that is like, well, the gravity is a gradient for all the orbits of the whole universe and all this kind of thing. That the punctuation, and it's most familiar to people, of course, with punctuation in the syntax of language. Period or stop or the decimal point or the radix point, the bang, the exclamation point, question mark, interrobang, those two together, octothorpe, the pound sign, these being less and less conventional forms of punctuation, that there's a comma and there's quotes and there's a period, and that was described as usually our punctuation in terms of anything to do with grammar, colon and the semicolon, the dash, the em dash, and all such varieties of quotes, and usually the printed material as with respect to natural language and its in its written form, and then also with regards to the syntax of bracketing and grouping and commas as joining and separating, or commas and quotes in the syntax of usually the programming languages, the formal languages, as with regards to those indicating a lattice, just like our integer points represent a lattice. And then it's also the same as with geometry's points vis-a-vis lines. So then the idea is to help establish that there's some concepts here that make for the walk integral. And so the path integral can be very intuitively understood as a line integral, like how long is a path? How long will an ant walking at constant velocity always on the path take, given that that's its velocity? what will result at distance, the line integral. Or from rolling a wheel, how many complete revolutions of the wheel will result as of this line integral, measuring it as via a wheel, or otherwise as via a means that on this line that this other surface actually makes the same amount of measure under all matters of scale and the affine and all this kind of thing. Right. So the idea is that there's these infinitely many higher orders of acceleration so that we get displacement with respect to time, velocity with respect to time, acceleration with respect to time, snap, crackle, and pop, or jerk, or variously those before or after one or the other, whether they're supposed to be like just some few higher orders that peter out, or the kind of like the end result with everything left in it assembled together. That this is like the rest of the long tail of this form, this infinite series that adds up to one in this hypercube dimension box that all falls back down. That the wave collapses like the hypercube box. The hypercube distance collapses equals to 1. And so the wave collapses more or less the same as equal to that. 1 in, 1 out, 1 across, 1 wide in 1 second. That's basically its frame. That's its meter. That's its little metric in what makes for it a space. So then the idea is that in the course of motion, there is usually applied either kind of a continuous change or the centripetal as of the moving of the feet. So this is the idea of the walk integral. It's like you're adding up a path, but each step you take is not exactly on a straight line, although you can make it as fine as you want. There are people who walk on tight ropes across high buildings. Then it can be no other than a very, very straight line. That otherwise each step, and whether it's up and down stairs or up and down the walk, is sort of a lurch. So the first kind of the idea of this punctuation is that in a path there'll be just these left, right, left, right, left, right, in the usual sense of the bipedal organism moving along in its feet, a lurch. So for this walk integral, beginning to introduce these terms where there's already kind of this category diagram of this stop derivative, which is moving down in the dimensions and bringing back all these sigmoidal things, Zeno swath, and a bunch of these other things that come into what starts making this hypercube box and its distance equals 1. Then through this walk integral, and then the pause integral is its complement, and then this run derivative is when things get going. That then it becomes very much so the linear motion. And this is going to make a sort of a category diagram of that those are kind of the changes, and then with the reversals or the inflections are the points or this punctuation. So this is kind of how I'm arriving at this theory of motion for mechanics with as few as possible, still like the least number of terms. I mean, we're dealing with, motion, rest, and equal opposite here as like the laws of motion. Coming up, or what need be these zeroth laws of motion that make the system of potentials underneath that of course resolve to the classical and the limits, and that they add up to it again on the outside. These are the kinds of things that help make for kind of these approaches. So we have this category diagram of sorts of walk, run, pause, stop. And now this walk integral starts being broken out as lurches. And so a lurch is just kind of when motion weighs to one side is when it would tip or topple, and then it lurches back. That there is basically a changing the weight to off weight is the usual means that a skier, for example, keeps himself aright, as well as making turns on a course in the alpine or Nordic skiing, where the alpine skiing is the downhill skiing and the Nordic skiing is the cross-country skiing. That the lurch then is just the idea that this walk integral is basically made up of these points that in more than less a straight line there is this. And then the steps are kind of made up of that, and then as regards to straight paths or turning paths or any sort of path according to motion, basically as a model of an anthropomorphized model of motion, that is kind of how it's described as this kind of thing. So for snap, crackle, and pop, and then jerk and jink or jank and those being kind of like when we have the motions of snap, crackle, and pop, it's like that's where the run up is and where the torque is, and how good and how static the torque is, and then also as with regards to on the rotational, when that let out, that for example makes the crack of the whip when it goes supersonic for that briefest of instants, or when the low energy side falls away, these kinds of things, vis-a-vis what results this main course of this object in all its orbits, that's only its linear path. So everything has been maintaining its own coordinate setting while living in this wider coordinate setting. It's still all perfectly compatible with the premier theories of relativity, and also with the quantum mechanics. It's thought of in the terms that that's how it must be. Well, it's yet only this kind of classical development that there's this qualification to make qualities of these higher orders of acceleration vis-a-vis the lower orders, and the smoothness and the circularness or the curviness vis-a-vis any kinds of kinks or straight lines in terms of changes, asymptotes. That this way it starts to build this kind of fuller vocabulary. Then with the vocabulary in a language to make some more of these features and terms for what's this zeroth laws of motion, for fulfilling Einstein's rotationally symmetrical, and as well with all of quantum mechanics as far as that comes in terms of Broglie-Bohm, all the way through, you see, into a holistic theory of motion, its mechanics, that then is got pretty much a lot of these other kinds of attributes of the fictitious forces or the pseudomomentum as understood, and having a placement in the mathematical model, so that then we can get to understanding the infinitely many higher orders of acceleration from an infinitesimal beginning, and whether that's the least jink, jank, or jerk, or it results in the snap, crackle, pop, figuring that basically that's what comes down one way and the snap, crackle, pop comes out the other way, is the idea to figure out an establishment of terms for these kinds of things, those being punctuations or gradiations, figuring that those are already existed and used as punctuations or gradiations, leave those same. And then you get into these ideas of like the lurch as a point, and then figuring that as with regards to like a step, or to have the step as the point and the lurch as the gradients of these things. So a few other closely related, highly technical terms are leaps and bounds, fits and starts, a hop, skip, and a jump. That's pretty much what I've come up with. And so fits and starts are when something is getting started and it hasn't really gained any traction yet until it gets started, and then as it does, it gains an impetus, it gains a means of going forward, it gains some traction in its power. And then the fits and starts, and then leaps and bounds, or is beginning to, when things start really moving up, that then it starts coming forward, and the lurch is no longer directionless, but like forward and over, and this kind of thing. And then a hop, skip, and a jump, of course, is related to either hopscotch style coming to a stop usually, or the triple jump going to the long leap, hop, skip, and a jump. So these are kind of introduced to be this work in terms of this punctuated motion, and then as with regards to the different places where this comes in effect, that then it would be as of a bunch of different perspectives on then anyway otherwise the track, the diagram of the path of motion, a motion arbitrarily, that all motion is relative, so that each is distinct, as with regards to any other object. That's, of course, being by the frames. Here, that's the frame space and space frame together. A nice little feature added to general relativity for this rest exchange momentum bit that makes for these Rama and Rama inner space frames and frame spaces. That this is sort of the accords of the milieu of objects that happen to be in motion. So what I'd kind of been getting into is that I've been introduced that now into my own little space of ideas. That among the idées fixes here, like the identity dimension, which is x equals y equals z, and or in any number of dimensions in a dimensional space, an orthonormal vector space of any number of dimensions, the identity line, where accordingly each of these coordinates is the same, and that then that all functions are defined in terms of it, that becomes a dimension, and then that relations as functions are defined both in terms of it and these semi-dimensions and them and it. That it's kind of like dividing by zero, but it's kind of like a singularity, and it's kind of like an envelope of all the integral equations that are so relevant to it. That's a thing. And so from that, then there was kind of developed this idea of the stop derivative, which is something is going to come to a stop. So if it's got these infinitely many higher orders of deceleration, at least they kind of reach till the end. It's like, and one. So then that makes this idea of the walk integral, which is like things go on their course, but somehow they always stay at the straight line. So this is the object in its frame. Then something that walks is in its own frame. Except, for example, like on a boat or on a train or up a hill or all these different kinds of ways. Then there's those other notions of integrals and derivatives as establishing summations over these infinite expressions, or the derivative as the inner scalar product, or as of instantaneous values in these things, framed neatly as they live in the language of real analysis. That then there's after these other ideas that were developed in the descriptive differential dynamics, or introduced, not really yet developed per se. They're developed when it's written in a few sheets of paper, and it will neither need nor matter whatever I say again about it, because as an enduring mathematical defense of themselves, these are defined objects then that just live in the universal language, the universe of the objects of mathematics. That then for this identity dimension is the idea of these drawing these functions usually in like the quarter plane, and then seeing how they cross that, and then so they have places above and below and above and below until they come out. And so these are the ideas, these points are where it crosses that. And so it's like, well, the potential is rising and falling and rising and falling as it's diminishing or increasing. But usually diminishing is simpler to figure out, because increasing just means it's changing direction altogether. These two kinds of things. Is to then make for this kind of form to start taking what otherwise are very well known and explored functions, like the periodic functions, sine and cosine, or any other kind of sinusoidal functions, or the hyperbolic sine and cosine to an extent, but those, as terms of being familiar and having well-known parametric forms, these equations in the coordinates, that to be attached to either sides of this identity dimension. Then the other key thing that I've been thinking to look at is with regards to the Bessel functions. So Bessel functions start to exist in the integral analysis, and they look like periodic functions to an extent, meaning that given a bounded region, it starts looking like just a ramp, like a line, and then it makes this sigmoidal line back and forth over that, and this is one of these paths to it, and the other one makes one with twice as many humps, the next one with 4 times as many humps, or that generally describes the shape of this function that the Bessel functions happen to have. So when you take a look at that, and then you kind of can imagine that being scaled out in a higher order, then it will make any number of these as of like a periodic function, but it's skew, meaning that instead of each of the functions being perfectly symmetrical about their crest and trough, they skew in the direction of this rent. So this is the way to look at that. Those are via a transform, one or the other the same. And then when it gets to where most of the character is in this hop, skip, and a jump, or these leaps and bounds as they start to grow, in terms of motion that arrives somewhere as of being directed, like at any given time interval, either a continuous amount of changes applied or a particular time interval as it's possible to ascribe a given fixed proportion or amount of change to it in terms of what can drive the path in these motions vis-a-vis natural potentials, that those as well have the exact same thing, basically walking through sand on the beach and always happen to step in a crater of sand and to step out of one too, and all these kinds of things. These are the kinds of things that I'm now getting into how to help describe that then as we make our way across this course, that it comes around and again this kind of diagram of these various ways to ascribe it to the mathematical models from exactly the same as usual physical models. What results then for all these notions of the continuous motion, what are aspects of changes of discrete motion? So that's what I've come up with today is lurch. Lurch is the word today, but it just means to it's not a gainly or graceful thing to make a lurch. It is instead as it's kind of like the dead weight of a motion. Yet it's to as well indicate that then in the model it's just kind of set, and so it is in my survey of the English language to find descriptive terms that aren't already in use and don't conflict with the others that come up with matching these same kinds of terms. This is about what I've arrived at so far. To match snap, crackle, and pop with jerk, jink, and jank, where that is perhaps slang, but it's added. And then there's vis-a-vis the juke, which is a particular sigmoidal movement as with regards to not colliding with something else, the swerve or juke. Not terms here, but perfectly apropos for what they describe. Then there's this idea of the lurch for this step, because otherwise that's just a step, a footstep, and it may be sometimes a stair-step. And then there's for the run derivative, of course, that's the run. And so then you can get into all kinds of descriptive terms, whether it's like the horse's gait or the person's gait, of all these kinds of ways that people make their ambles and these kinds of things. That then there's snap, crackle, pop, and jerk, jink, jank. And then there's this lurch, and then making for leaps and bounds as those gain and run up. When something runs up, it starts to get running. In terms of these being the terms, and they're the same ones from natural language, then there's this hop, skip, and a jump. And there's one other brief one, but mostly it was the leaps and bounds that adds up for this rest exchange momentum to help explain why something gets going and then going and then going again, as for example from fits and starts on up to smooth running and this kind of thing. Then the idea with the punctuated motion is that in these forms, according to like the regular and the periodic or the skew periodic, and then about the identity dimension where very particular functions just kind of cross it, and like a Poisson distribution, they're more likely and then less likely and then less likely and then peter out and stop. That these end up making for descriptive that then according to these distributions, that it's these same distributions that end up making for very naturally things go in their most natural seeming, most graceful forms of motion. Well, let's see what the books have today. Let's see here. There's much to be read yet in the story of philosophy. So this was Will Durant's bestseller from 1920, or it had printed more than 10,000 copies. So he talks about contemporary American philosophers, numerology of sorts, and what people make of it. Talks about Kant and Bergson. So then we can kind of separate it as the end of idealism and the beginning of existentialism, in a sense. To rescue faith from the universalized mechanics of materialism. And I don't have much for Schopenhauer. I just don't really. I'm not a Comtean. I don't care so much for the logicist and positive movement, except that my theory is very strongly logicist, and my science is very strongly positivist. So a lot of things that I have attached to it is like the ennui or the angst, and going back to the cyclic metaphysic, like the deal with the anti-Plato and all this kind of stuff. I just don't find it so relevant. I can understand that they are relevant and they're a given, and for many people they're a necessary thing because that's what they've attached to it. Otherwise, what needs the place of these things? Kind of when we were talking about Jasper and his provision, this kind of thing, and then that got into the soul and this and that, vis-a-vis empirical materialism and this and that, which is a real thing. And then at the end here, he discusses Dewey, John Dewey. So he was a very voluble man, and he got into a bunch of stuff about education and is very American a thing. And so the Dewey Decimal System, I think, is most familiar to people as this is how all the books in the library are given a number, because he's made an ontological category for every single section of the library and broken it down section by section in the section into all these kinds of things. Then in the University Library today, there's a different system. It's like the Library of Congress catalog system, or the one for the universities. It was quite profound, the subject classification. When first encountering a great grand library, it was kind of like you can peruse and browse all the stacks you'd like, and each one has its own little number, and they kind of fit in a row, and you learn that they don't always live in that order, and there are greater and lesser books all among them, and there are different sorts of works all throughout, but still it's a great thing. Real education comes after we leave school, and there is no reason why it should stop before our death. What distinguishes Dewey is the undisguised completeness with which he accepts the evolution theory. Well, now evolution theory is like, some people think that that's only survival of the fittest, or the Darwinian evolution and this kind of thing, but there's much to be said that animals that cooperate are not necessarily acting in their self-interest, except with regards to their self. I was reading this book about identity, and it was by a fellow named D. Berreby, I believe it was, Berreby, if I'm not mistaken. And he makes a good point that, first of all, he kind of lays into the Darwinians as, and with regards to gold and the infamous debates between Gould and Darwinians, or some of these other creatures of the social sciences or social studies world that amused me quite a bit. When Descartes said the nature of physical things is much more easily conceived when they are beheld coming gradually into existence than when they are only considered as produced at once in a finished and perfect state, the modern world becomes self-conscious of the logic that was thenceforth to control it. So that also gets into, it reminds me of Dehaene's book on the number sense and this development in infants, and the idea that infants can tell when something is gone, like peekaboo or surprise, something disappeared, really registers on them because they're able to that their reality, according to their senses, is so shocked by the incongruity. Vis-a-vis things that are introduced or leave are kind of more part of the background of all sorts, that it's something. Kantian categories, even Spencer believed that the Kantian categories of habits and forms of thought were native to the individual, whereas in all probability they're merely a product of the social transmission of mental habits from adults to children, which is almost completely matters of imitation, of course. Imitation is the great experiment where you try to figure out if just by the fact of imitating your peers or influences or those who are expecting to get out of you an imitation or a stimulated response, these kinds of things. We must unlearn our ideas about an unchangeable human nature in an omnipotent environment. Well, and to extent, there still needs to be one. So, that's that. Yeah, Dewey. Dewey is he's kind of an agitator. Dewey distrusts the state, which is a pluralistic order. So he's like, voluntary associations. It may be a great utopia. But he's very American, and very well regarded as an educator. So this book basically ends on that. So that's surprising. One of my favorite educators, or what I thought was, and another bestseller at least, is in the 80s and 90s, one of the best-selling authors for youth was Piers Anthony. And so Piers Anthony Dillingham Jacob was an Englishman, and he emigrated to America, and from what last I heard, he's a Floridian, and with his family in Florida. But what I knew him for were all these books that he wrote, all these books. And so Asimov had like 20 books of nonfiction at least. I've read 20 or 30 books of Asimov and 10 or 20 more of his pieces of nonfiction, all of which are great. They're just fantastic. Heinlein is an example of a science fiction author. This is probably most of my interest, science fiction and action adventure of a sort, and a thriller in a sense. The novels of the time. That then for Heinlein or something that compared to like Clarke, Arthur C. Clarke, comes across not really that great or profound. Voluble and quite full of himself and science, very very hard science oriented with the eyes to the skies, and in 2001 was made a very very great cinematic experience to be sure, but then there was and then like Anderson and many other authors of the time like Ludlum and Cussler and the action adventure spirit or all these matters of what was popular mass market youth oriented material at the time. But Piers Anthony had these many great series in the magical and the science fiction too, and they say that science fiction and magic are indistinguishable at sufficiently high tech levels or power. Well, whereas of course we know that that's plainly the realm of the fantastical, and it can stay there. But it is as well the plain realm of the fantastical, where it is always there. So what I thought to make a mention of that was for some aspect of one of his works. And I recall what it was about. And so in one of his short stories, he wrote a story about a car race. And so what it was is this was unlimited and open class, and what was in it was a race of the best of breed of each of these kinds of motor trains of the vehicles. So you had internal combustion versus electric versus the great steam versus compressed air. This runs off springs. And then someone was driving nuclear fission. And so over the course of 10 or 20 pages, then in this book, I mostly appreciated the guy's taste quite a bit, and his willingness to at once give everything to the characters, like from his science fiction series, or as the various series with regards to Xanth, A Fantastic Land, or as with regards to the Universal Cluster series and these kinds of things, and his short stories and such. Yet that this one, and then in this one, many of these issues of the transmission of power and the development of motive force and the motive power, like a locomotive, and all these things really came to bear, and it reminded me of that. Now, in that example, the nuclear fission one, yet it's not something necessarily that would always be so, except as with regards to the configuration, space, and the scale and energy of experiment. Otherwise, one of the great science fiction writers of the time. So I was kind of reminded of that because I picked up this book today, or these pieces of this book, which together form a book with a little bit of tape, say. This is called the Yearbooks of Facts, the Yearbook of Facts. Well, what year is it? It's 1846. And what I've been able to peruse so far from this book is they get talking about things like, how do we get this locomotive on this railroad moving up the tracks? And furthermore, how do we take our building and make pneumatic tubes everywhere through the building and send our letters and parcels and posts through the building by this great array of the capillary action of pneumatic tubes. And so what they call that here is something with regards to intercepted atmospheric pressure. There's described, for example, the usual chimney effect or draft, and as with regards to how it kind of exists according to pressure differential and a capillarity action, whereas everybody else knows this because heat rises. And so I was like, wow, in 1846, this is a pretty interesting discovery. The tube was represented to be 180 feet high without the cap or intercepting plate. And so maybe it really was just heat, but they describe it as also the secondary consideration. Then as with regards to the steam engine, they talk about, the steam engine's got its triple point and like a live steam and then a soft steam and hot steam and cold steam. And it talks about the difference between about these locomotive or stationary engines and about the elasticity of air. And so what got involved by the patentee, Mr. Parsi, for the power of condensed air, there was to obviate the excessive force and gradual design, the inductive passage from the high pressure, that is described that by having a much larger volume piston, that it was this kind of this opposite the capillarity action. Like, why does a boat rise in the why does it have buoyancy? That it's that instead of like a much smaller piston made it so that then it became much smoother, the application of the transmission of the power and the generation of the motive force. So when I saw that, I thought that was kind of relevant to this discussion, and then it reminded me of that story. So when I picked this up, I thought it was quite interesting, and it's from Fleet Street, in England, and here it gives, for example, how to define what is a gradient for a railroad, as with regards to what would be the resistance per ton of, according to the wheels, their radiuses and their speeds, that in such manner some moment in motion, that these different means of generating, storing, transmitting, and transforming the application of motive force have quite a significant amount of empirical backing to be accommodated, as with regards to this study from 1846, largely of railroad and railway technology vis-a-vis the caloric in the air pump, for example. What's that we recall? Well, what we recall is that's an obsolete thing replaced by the theory of Chaleur and heat. And our perfectly great theory of Lord Kelvin's second law of thermodynamics, the statistical ensemble, and how that works great with all our other theories together. So then when we get back to this ideas of like, what actually defines the caloric, and with regards to the maximum uniform or mean velocity, these matters of the empirical and the tribological, and with regards to such, made up by grouping a number of velocities registered in the tables, was advanced as an inconsistency with regards to the height of the barometer. This gets into like quite a few varied concerns that then one would figure to make a very, very closed set of definitions, so that the inputs are reduced from the infinitely many sum of histories, sum of potentials, to arrive at what could be descriptive and such. The tractive force fits and starts the tractive force. So I saw this today, and it very, very well amused me. I'll look to that some more later. See, there's a copy of Griggs Hegel. There's McKeon's Aristotle. This is a book. It's just a primer on integral equations, or primer. In this textbook for students of the physics and mathematics departments of colleges and universities, the problems and exercises in integral equations, translated by George Yankovsky, by Krasnov, Kiselev, and Makarenko. Mir Publishers, 1971. Mir is Russian for peace. So it's got Volterra, it's got Fredholm. And these today are, when you look at the Wikipedia page for integral equations, that is what they got. The Bubnov-Galerkin method. So these are approximate methods. It's got some numerical methods for integral equations. The Ritz method, Kellogg's method. Singular integral equations of the first and second kind. Integral differential equations, Euler integrals, Abel's problem. The method of successive approximations. Convolution type equations. Using Green's function in the solution of boundary value problems. Convolution type equations describes that phi 1x and phi 2x are two continuous functions defined for x greater than or equal to 0. The convolution of these two functions is the function phi 3x, defined by the equation phi 3x equals integral from 0 to x phi 1x minus t of phi 2t dt. So this is a much simpler definition than what we got from Neri. Let's think back to some many talks ago, and there was reading about the convolution and Neri's singular integral. And so this is the same definition on the inside, but it's a little bit simplified with regards to the whole apparatus of the functional analysis and all that. It's kind of reduced to, like, the non-negative numbers, and it helps to explain that then this bound about x minus t and t is that this is like this one coming this way and this going the other way in a bounded region. So the convolution is taking two functions, setting them against each other, and then multiplying them together. And so the idea of these orthogonal functions like sine and cosine, they're like, it kind of are always convoluting each other. And then these orthogonal functions in those particulars. And then you can take any two functions though and kind of convolve them in this way. So this is a great idea to kind of add with some of these other concepts here, the convolver of making it here. That then for these Bessel functions is the idea is like these Bessel functions are going to convolve either way. These periodic functions are going to convolve either way. Then was with regards to what ends up making for the attenuative and dissipative and the oscillative and the restitutive makes the constitutive. So the constitutive and the annihilating, those being algebraic. That this is amusing me a little bit to then relate that as in so few terms, then how to get these put together. Abel's integral equation and its generalization. So a particle is constrained to move under the force of gravity in a vertical plane along a certain path. It is required to determine this path so the particle, having started from rest at a point in the curve, path with ordinate x, reaches the e-axis in time t equals f1 of x, where f1 of x is a given function, figure f1. So it's basically for a tautochrone or an isochrone, how to control, as it puts it, or constrain under the force of gravity to reach this. The absolute velocity of moving particles, so it gives that it's going to be falling at least as fast. Denoted by b, the angle of inclination of the tangent to the axis. The angle of the tangent to the curve to the x-axis. Then we have d8 over dt equals negative root 2g. It's quantity x minus eta. So as if it's kind of convolved to eta sine beta. Whence dt equals negative d eta over root 2g x minus eta sine beta. So it gives dt by itself the raw differential. Integrating from 0 to x and denoting 1 over sine beta equals phi n, we get Abel's equation. Integral from 0 to x phi eta d eta over root x minus eta. This bring in mind both this convolving and then like x squared plus minus 1. And so if x is root x squared there equals negative root 2g times this quantity f1x. Now it doesn't explain how to get all these things. The required curve is defined by the parametric equations eta equals big phi 1 beta and eta equals big phi beta. Thus, Abel's problem reduces to a solution of the integral equation fx equals integral from 0 to x of kappa of xt phi t dt. The given kernel k, kappa xt, given function fx, and unknown function phi x. In other words, it reduces to finding a solution of the Volterra integral equation of the first kind. The following somewhat more general equation is also called Abel's equation. Phi t over x minus t quantity squared dt, the integral from 0 to x of that equals fx. So that being the parameterization and the implicits going into these integral equations, I'll be trying to think about that some more. So with regards to Volterra and Fredholm, because I kind of need to revisit Volterra and Fredholm, and then as with regards to Volterra and Fredholm on the side of the integral equations, being like these are the most well understood and developed forms. And then Sturm-Liouville from the side of the differential equations, for these would be anonymous, to help to try to start figuring out some more of these things to help figure them out in terms of the implicits of each other with regards to boundary value problems and singular value problems, initial value problems, and these kinds of things with regards to the initial and singular and boundaries and this and that and cycles. Integral equations. So This is just a great textbook. It basically sits with this these university texts. Here, I'll put it here with the university texts. York Cantor, Abraham Lincoln. Hegel is thoroughly enlightening. Hegel is he's got both the great story. I mean he knows about railroads and the latest developments of 1846. And here, for example, Griggs in his preface, or this is W.T. Harris, Washington, D.C., August 1890. As early as 1858, I obtained my first insight into this philosophy, studying Kant's Critique of Pure Reason. So Critique of Pure Reason at least gets into that there is reason. It's subjective. We start being subjective, and you learn enough of that, and then you mature mentally and philosophically to be where it's like, I am both objective and subjective, and this kind of thing. And this with regards to the absolute wonder and beauty and truth of pure reason, and you know, res and ratio, that all such things make perfect sense. It was in 1864 that I obtained an insight into the logical subordination of fate to freedom. The totality of conditions cannot have a fate outside it, but must be spontaneous in itself and self-determined. Hence all fate and all changes not spontaneous must be secondary and derivative from a higher source that is free. See, that's a great way to put that. I'm glad I've read this preface to Griggs Hegel, these few words. An ardent Fichtean. In 1866, I arrived at the first insight that is distinctively Hegelian in the most important aperçu of Hegel's logic, that which is appertained, that which we may attain to. I wrote this out in a letter to my friend Adolf E. Kroger, an ardent Fichtean, whom I had discovered and was endeavoring to proselyte for Hegel. So Fichte preceded Hegel, and Fichte in his writings came up with a bunch of the dialectic. So we often will give to Hegel and say the Hegel modernly is kind of our modern author of the dialectic, specifically the synthesis and antithesis synthesis, or in reverse, the thesis, antithesis, and synthesis. So Fichte may have come up with that, and then Hegel kind of adopted that. And then otherwise, Fichte is not so popular because he was pretty stiff and not very likable in some senses. I called it the distinction between comprehension or begriff and idea or idee. So sometimes we have that there's what's called intelligentsia or knowledge, and then there's the scientia or science. And so what is understanding, or intelligence is called understanding, and then knowledge is called science. And so the begriff or idee, or like when we were talking about Frege with like the idea or thought or these kinds of things, that the understanding is the uninformed, a naive view of knowledge, and now overgeneralization is generally unsound. So it's not to be said that understanding means not understanding. That understanding means just saying I give up and what do you think, you know, or I don't know, and but it depends, and this kind of stuff. It does. That's an understanding. Then there's knowledge is kind of as matters of scientific fact. You know, we kind of got our techne and our psyche. You know, both. And these kinds of things that in the mental and philosophical maturity involves kind of getting up and coming up through this, and you know, having some, if not skepticism and cynicism, at least knowing what those are and what they would mean to exist for these kinds of things. That it gets quite airy up there. It should really be the distinction that Hegel makes between negative unity or substantiality and begriff or idee. It is undoubtedly Hegel's highest thought. It is the insight into the nature of true being, to be altruistic and to exist in the self-activity of others. Indeed, one will have arrived at that at some point in time, even if only to protect themselves from others. The Life and Times of Aristotle. Alexander's teacher. If a body has sensation, it must be either simple or compound. And simple it cannot be, and compound it cannot be. He has some great didactic deliberations. We shall, after describing the other states, distinguish as two kinds and say how each of them is a mean. And similarly, we shall treat also of the rational virtues. Very well said. Well, all right then. I shall suppose we will arrive another day at more about moment in motion. Today's being about punctuated motion, introducing the terms of snap, crackle, and pop that is among the higher orders of acceleration. Go with jink and jank as of everything from spinning rods and fouling them up to the last little dot that crosses the T. Lurches, leaps and bounds, hop, skip, and a jump, and all such manners of moment in motion. Geometry is motion.